This session was designed to be of general interest, in particular to the permanent delegations of UNESCO. And speaking of permanent delegation of UNESCO, I'd like to welcome a former head of permanent delegation to UNESCO, Dr. Ali Al-Mashad, who was the ambassador. So Ali, why don't you stand up? So everybody can see you are here. Ali Al-Mashad was ambassador representing Iraq to UNESCO for many years. But he's also a very good example of the application of space technology to modern society, because he founded the Arabsat organization, and he was the Director General of Arabsat for many years. So thank you very much, Ali, for your contribution. We will now move to the keynote speakers, and I will start by introducing Professor Armin Grün, who will give the first keynote. Professor Armin Grün was, since 1984, professor and head of the chair of photogrammetry at the Institute of Geodesy and Photogrammetry of the Federal Institute of Technology, ETH, in Zurich, Switzerland. Since the 1st of August 2009, he is retired and is now with the Institute of Conservation and Building Research of the Department of Architecture at the ETH. Currently, he is acting as a principal investigator on the simulation platform of the Singapore ETH Center Future Cities Laboratory in Singapore. Professor Grün graduated in 1968 as diploma engineer in geodetic science and obtained his doctorate degree in photogrammetry in 1974, both at the Technical University of Munich in Germany. From 1969 to 1981, he worked first as a research and teaching associate, later as chief engineer at the Institute of Photogrammetry and Cartography. From 1981 to 1984, he acted as an associate professor at the Department of Geodetic Science and Surveying of the Ohio State University in Columbus, Ohio, United States. Professor Grün has had lecturing and research assignments at various universities and research facilities in Germany, Australia, China, Finland, Italy, Netherlands, Russia, Switzerland, Taiwan, and the United States. Professor Grün is a member of the editorial boards of several scientific journals. He has published more than 400 articles and papers, and is editor and co-editor of over 21 books and conference proceedings. He is a corresponding member of the German Geodetic Commission in Munich, member of the German Archaeological Institute, honorary professor of the Wuhan University, Wuhan, China, and Yunnan Normal University, Kunming, China. Honorary member of the Japan Society of Photogrammetry and Remote Sensing, fellow professor at the Center for Space and Remote Sensing Research of the National Central University in Taiwan, visiting chair, professor national Chengdu University, Department of Geomatics, Tainan, Taiwan, and honorary member of the International Society for Photogrammetry and Remote Sensing, ISPRS. Professor Grün, you have the floor.
Good morning, honorable guests, dear colleagues, ladies and gentlemen. It's a great pleasure for me to be here in this respectable place and to talk about something which is very close to my heart, indeed. It's not only about the job and the subjects, it's fun to a certain extent to work in this area where we combine high technology space technologies, with history, with cultural and also natural heritage. Now, I will talk about the use of satellite images, but I also go a step further and will use aerial images, terrestrial images, laser scans, and so forth, because all relates to cultural and natural heritage. Now, how do we go about the generation of these three-dimensional models? We use images. In this case, we use aerial images, a minimum of 2 aerial images, and from those images, there should be a link, a video link. From those images, we derive models, three-dimensional models, which include geometry, which include texture, which also may include semantics if you put it into a spatial information system. For instance, this is, by the way, our campus of ETH Zurich at Höngeberg. This goes back to 2004. So every tree has been measured and modeled, has a correct height. There's an underlying digital terrain model, and texture has been generated on the roof and on the terrain fully automatically. Can we continue? It's a bit difficult because normally I control my presentation myself, but now I have to communicate with the center. Can you stop the video, please, and continue with the PowerPoint? Okay, so I said before, we are using different platforms. We are using, of course, satellite platform, aerial platforms. We use more and more UAVs, drones with very high resolution. I'll show you 1 or 2 examples. And of course, we use terrestrial sensors, images, but also laser scanners. And with these sensors, we can produce landscape models, very large cultural, natural heritage models. We can produce city models. This is what I do currently, primarily in Singapore, working for a future cities laboratory for architects and city planners. And we can generate smaller items. Of course, not from satellite images here. I also will show you a few examples addressing the statues and so forth. So how do we do it? We collect images, in this case from our NASCAR project, from the modeling of geoglyphs. We collect a set of aerial images in the order of 1,000, in this case, very large format images. From these images, first we do a georeferencing, a very precise positioning of the images down to the centimeter level. And from these geo-registered, geo-positioned images, we derive digital surface model. And then we go a step further and do what we call an ortho image. This is a transformation of the aerial image into the geometry of the map. So it's consistent with a map, you can overlay it and geometrically it's correct. Now you can combine the digital terrain model and the texture, the ortho image, and you practically have a 3-dimensional image, which you can fly over, walk through, inspect. Now, in addition, you can visualize it, you can animate it. In addition, you can derive vectors, 2-dimensional vector data, 3-dimensional vector data, and also overlay. And then we go a step further and we collect existing data from previous archaeological studies, for instance, historical information, and everything together goes onto an information system, geographical, cultural, building information system. This is how it works. I'm not going into more technical detail. When I talk about geodata, of course, Google Earth is very much familiar with you. And if you look at Google Earth, for instance, if you look at Switzerland, you find very high resolution images, which in this case are not from satellite platforms, but from aerial platforms. This is very fine, this is okay, this looks good, but if you look at the digital terrain model, it's very strange. This hill is about 30 meters high. It's next to my home, close to Zurich, but it does not exist in reality. It only exists on Google Earth. So Google Earth is using the SRTM dataset, old interferometric radar dataset, and in some areas of this world, it's very bad quality. Errors are going up to 100 meters, 200 meters in mountainous areas. So if you don't know the situation, you accept it, okay? You only will know if you are living close by, if you know the area. So be a bit careful with Google Earth data. It's nice for touristic purposes maybe, but surely not for professional purposes. So we aim at much better accuracy. This is an example of AFNIR, a JAXA project where we used AFNIR 30-meter footprint data in order to produce a three-dimensional model of central Switzerland. But we are going more and more into higher resolution. And now we are in Bamyan, in Afghanistan. Later on I show you a bit more about the computer reconstruction, not the physical reconstruction of the Bamyan Buddhas. But we also have not only reconstructed the Bamyan Buddhas, very high resolution, but also generated a digital terrain model of the environment using Spot 5 and overlaying it with Iconos texture. So the texture has a footprint, a resolution of 1 meter. And if you look at a rock face here, which is about 1 kilometer long, to the left side you see the big Buddha, and to the right side the niche of the small big Buddha. And if you can see even from space, you see that the niches are empty, that the Buddhas are destroyed. You can have a look at the flyover. Sorry, can you go back once more and activate the video? So in order to prove that this is really a 3D model, and I repeat, it's been derived, the digital terrain model, from Spot 5, stereo data, and the texture from Iconos, 1 meter resolution. So there should be, okay, we skip it for the sake of time. Somehow, I don't know why it doesn't come. Can you go to ASRock? Yeah, here we are, and start the video right now. This is ASRock, which again has been produced from aerial images, 2 aerial images. Such a model we can do nowadays fully automatically. And such a model with this resolution we can do also from satellite images. The only thing is this has been done 15 years ago, and at this time we didn't have the very high resolution satellite images that we have nowadays. This is used a lot in Australia by teachers to introduce their students into their natural cultural heritage without going there. Okay, next one. We can stop it. So again, I repeat, such a model we can do nowadays fully automatically. And this is Cochicalco in Mexico, pre-Inca. Pre-Columbian, I should say, pre-Columbian settlement. And this includes, it's a bit more complex, includes a number of buildings, man-made constructions, and also derived from 2 aerial images. And this you cannot do fully automatically. We are using semi-automated technique to generate such a model. Just to give you an idea, for somebody who is familiar with the technology we are using, this is a work of about 3 to 4 days. So again, the link doesn't work. I don't know why, so we continue. Just believe me that this is a 3D model with underlying digital terrain models and the man-made structures on top of it. Now we talk here primarily about satellite data, satellite images, and here you see the development from Landsat 1 which was 80-meter footprint to Worldview 3, for instance, which is supposed to come with 30 centimeter. And with 30 centimeter, of course, you are in the domain of aerial imagery already. So you can do a lot of interesting stuff. We were supposed to model Machu Picchu, not only the landscape, but also the buildings. But for the buildings, unfortunately, resolution is not good enough. So what we did, we used old aerial images and we derived, okay, sorry, this was meant to be a video. Can you go back and hit this one? Yeah, ESN flyover. No. Something doesn't work. The video, no, the other one, sorry, the other one. Yes. So here you see the dramatic terrain, the digital terrain model in Machu Picchu, as it has been right in the terrible road that leads up to the site. This has been derived from aerial images. Now, even aerial images, which have been scanned at about 40 centimeter pixel size, were not good enough in terms of resolution to do the buildings. So we had plans to fly a UAV, a drone over Machu Picchu, but we couldn't get a permission to do so. So we did not model the buildings. Here you can see the resolution is just not good enough. Let's continue. Now, if you use images, you can go back in time. This is an example of Tucumán in Peru, where we used old aerial images from 1949, Fairchild camera, and of course, especially if you have adobe structures, which are decaying very quickly over time, it's interesting to go back in time and to compare what happened in the meantime. So what you see here is a model, fairly high resolution of Tucumán, as it was in the year 1949, and very clear you can compare now with the current situation and do your analysis and your studies. Now we come to aerial images, and there are different platforms. There are surveying aircraft, there are balloons, there are UAVs or real helicopter, manned helicopters. And one interesting project we have done after we produced in the year 1985 a new map of Mount Everest on request of the National Geographic Society. So what I did with these were analog aerial images flown over Mount Everest. I scanned them and I produced a digital terrain model. And can you hit the image, the Mount Everest on the left side? Just click, no, this one. No. And out comes a very high resolution 3D model of Mount Everest with about 10-meter digital terrain model spacing and 1 meter texture, 1 meter pixel size. Of course, nowadays you can do this even better with satellite images. You can produce 0.5 meter pixel size, clearly. But at this time, those images were not available, so we used aerial images. This model has been used a lot by geoscientists, by mountain climbers to prepare the mission, and so forth, and by animation people. And you can also go ahead and overlay. You can play around now. This is all digital data. You can overlay an existing map, the analog map with the red lines are the different ascension routes. So you have the map in 3D. Now we come to Nazca, Peru, to the geoglyphs, and we had a project there where we measured in 3D about 1,500 geoglyphs, and I show you quickly just a model. What you see is not an aerial image. This is a view onto a 3D model here, and we can do a flyover. Can you click left? A flyover, and you can overlay the vector data to the right, as I have explained earlier, This is a flyover over the model, and of course you can stop anywhere. Interactively you can zoom in, what you cannot do in reality. So this is of great value to those people who are working on the Nazca lines from an archaeological or art historical point of view. Okay, and from this data, digital data, I'm always surprised. We have a wonderful digital data, and then the archaeologist comes and says, can you give me a map? Okay, a traditional map. Yes, we can give him a map. So this is a map that has been derived from the three-dimensional model. Can you click Salzburg? Now we come from modeling of nature, we come to city modeling. And this is a 3D model which we did for the city of Salzburg. It's used for public relation, for touristic purposes. And this is about the standards that you have, at least in Europe now, in 3D city modeling. So this is derived from aerial images, vertical aerial images, plus oblique helicopter images. In a semi-automated mode. Please skip this one, skip. Yeah, now we come from aerial sensors to terrestrial devices, and as you can see, we not only have imaging devices, we do a lot of work with mobile phones, with mobile phone camera. You can do a lot of work nowadays with such cameras, but they have to be calibrated, of course. But you can use laser scanners as well, you can use panorama cameras. Now, we did a 3D model of Bet Georgis in Lalibela. I continue quickly, and this is a very interesting project, which I'd like to present. There are two pieces of what's called the Veri Paracas. One piece, the lower part, is in the Antalya Museum, and the upper part was in the Boston Museum of Art. The Turkish government claimed that they belonged together originally, and that the torso was brought out of country illegally. Now, how do you check this? We offered our service to model, to scan both parts and to put it together on the computer and see to what extent they would fit. We received permission from Turkish government, and we modeled the lower part, but we were denied permission from Boston Museum. Now you can think whatever you want. In the meantime, by the way, the torso is back to Antalya, and both pieces are back to Antalya. That's a good news. So this model has a surface accuracy of about 50 micron. 50 micron, 1/20th of a millimeter. Now, Bamiyan, Afghanistan, we used old images, pre-demolition images, in order to reconstruct the great Buddha. Here you see the details, very much in detail, the folds of the dress are about somewhere between 5 centimeter and 10 centimeter wide. So we were able to measure the Buddha, to reconstruct the Buddha. Can you please call the video. With an accuracy of about 1 centimeter, 1.5 centimeter. Okay, so you see it's a 3D model. Next one. And we also modeled the empty niche. And if you, on the left side, you see the empty niche as it looks right now. And the right side is a reconstructed Buddha. But you may also be able to see the frescoes, the frescoes that have been there before it was destroyed. So we also reconstructed the frescoes. We also worked on the small Buddha. In the meantime, we have a 3D model of the small Buddha. We did the whole rock facade, which is about 1 kilometer long and very high resolution, using photogrammetry, terrestrial photogrammetry. And we built up a kind of information, cultural information system of the whole site. There was a movie, The Giant Buddhas, of of Christian Fry, where he used our data for animation. So in the final scene of this movie, the great Buddha would be there anymore, again, not anymore, would be there again in form of an animated model. It's quite impressive if you have the chance to see the movie. Let's go further down to UAV technology. There are hundreds and hundreds of different systems available nowadays. We're using UAV since about 10 years, 2004. This was our first system, a model helicopter equipped with GPS and IMS, stabilization platform, autopilot, and a camera of your choice. So it runs fully automatically. You only start manually because navigation system is not so good. You start and you land manually, but the mission is pre-programmed and is done fully automatically. We also use this octocopter, Falcon 8 in particular in Singapore these days. And there's a list of projects which I skipped for the sake of time. So we have used UAV technology in many different applications under many different circumstances. For instance, in Bhutan, where we kind of modeled the first really serious archaeological excavation. On the left side, you see me standing on top of what's called a dzong. And on the right side, you see the excavation status, archaeological excavation, and the trees are all cut. This was only possible by a permission of the king himself. In Bhutan, as you probably know, you are not allowed to cut any tree without permission, and here we had to cut quite a few. So it went all the way up to the king to have a permission. And we flew what's called a quadrocopter. We couldn't fly a helicopter here. We are operating here at 3,000 meter altitude. In a mini helicopter with a gas engine, there would not be enough oxygen. There would also not be enough uplift. So we had to use a much smaller, much lighter device and had a lot of problems. But finally, we collected our images and we combined the model of the excavation, which was derived from UAV images, with a model derived from satellite images. So the area around is all from satellite stereo images, while the walls, for instance, are at very high resolution. We work currently, as I say, in Kopan. In Kopan, we combine satellite aerial images, LiDAR, with terrestrial laser scans. We also go into museum and scan statues that have been brought aside and put into different museums worldwide to bring it back on the site. Another application of satellite images is city modeling. Normally we use aerial images in city modeling, but Singapore aerial images are highly classified. I've been there for about almost 2 years, but I've never seen an aerial image. They're highly classified. Even said for satellite image acquisition, you need a permission from government, from the police, which we got in 2 areas, Little India and Punggol. Punggol is a new area with totally new buildings for 360,000 people. And we used Iconos in Little India, and in Punggol we used Worldview 2 for producing a city model. Can you click quickly? Left side. So this is what you get from Worldview 2, from 50 centimeter resolution. This is used by our city planners for certain studies, city modeling. Texture, again, is also from satellite image on the roof and on the terrain, not on the facade. This was not necessary in this case. Okay, next one, we are almost through. This is a final model which includes digital terrain model, which includes buildings, which includes trees. We measured 2,000 trees in 3D and other man-made objects and so forth. Now, this is the last one, previous to the last one. This is our ongoing project. I just want to show you exciting island, French Polynesia, Moorea. This is in general sense, an environmental modeling project which is driven mainly by biologists, but also many other experts involved. They call it Island Digital Ecosystem Avatar, and we have ordered tasking for Pleiades images in order to produce a 3D model of the area, also of Tahiti, by the way, and Terra, a smaller island in this area. So this is a typical example where satellite images, high resolution stereo satellite images play a very big role. This is ongoing work. And finally, I would like to conclude and express my acknowledgement for the fact that cultural heritage and space technologies are going well together, in my opinion at least. You can bridge space and time. You can go from early man to ESA's Planck telescopes. We worked also on the deformation measurement of the Planck telescope at very high accuracy. And it works from Mars mapping to nanotechnology. Thank you very much for your attention. Thank you.
Thank you very much, Professor Brun, for your very exciting presentation. I'm sure that many of us will want to discuss with Professor Brun some of the projects that he has alluded to briefly during his presentation, and invite you to use the lunchtime and coffee breaks to ask him any question that you want to. And I would like now to move to the second keynote speaker of this session. The second keynote speaker is Mrs. Barbara Ryan. Barbara Ryan is the director of the Secretariat of the Intergovernmental Group on Earth Observation, GEO, located in Geneva, Switzerland. Before assuming this position in July 2012, she was the director of the World Meteorological Organization Space Program. She had responsibility for the space-based component of the WMO Global Observing System, coordinated space-based assets to meet the needs of WMO members in the topical area of weather, water, climate, and related natural disasters. She also served as a technical focal point for WMO's activities with GEO. Before joining WMO in October 2008, Barbara Ryan was the Associate Director for Geography at the U.S. Geological Survey in Reston, Virginia, where she had responsibility for the Landsat remote sensing, geography, and civilian mapping programs of the agency. As the 2007 chair of the International Committee on Earth Observation Satellite, CEOS, she led the Space Agency response to the Global Climate Observing System satellite requirements for sustained measurements of the GCOS essential climate variables. She holds a bachelor's degree in geology from the State University of New York at Cortland, a master's degree in geography from the University of Denver, a master's degree in civil engineering from Stanford University, and she was recently awarded an honorary Doctor of Science degree from her alma mater, the State University of New York at Cortland. Barbara, you have the floor.
Well, thank you very much. It's a pleasure to be here this morning. Let's see, I would largely like to build on the last presentation about really linking observations and users. We'll go to the, so I can control the slides from here or no? Just, okay, great, thanks. Listen, for those of you, and I imagine there's still a couple in the audience that don't know the group on Earth Observations, we were really created about a decade ago to in fact build, create a coordinated, comprehensive system of systems. We happen to call that GEOS. It's in these, the original focus was in these 9 functional areas: agriculture, biodiversity, climate, disasters, ecosystems, energy, health, water, and weather. Following the World Summit on Sustainable Development in Johannesburg back in 2002, industrialized nations came together and said, you know, as a community, Earth observations have done a really good job down in weather about coordinating Earth observations globally. How come we don't have those successes in these other societal benefit areas? So today I'm going to just focus on one of those areas, and that's agriculture. But let's go to the next slide and you'll see. So essentially, just 4 objectives: improve and coordinate observation systems, advance broader data policies. I won't talk a lot about that in this presentation. It'll come up in some panels later on in the week. But foster the increased use of Earth observation data and information. And if we go back to Len's presentation a few minutes ago, that is exactly what's being done. It happened to be in the archaeological arena, but we want users to uptake this data more and ultimately to build capacity. So where are we today? Took a couple years after 2002 to actually stand up the organization. This is what it looks like right now. 91 member countries, pretty good coverage in the Northern Hemisphere, some substantial holes, largely in the Southern Hemisphere, South America, Africa, the Middle East, a fair number of Pacific Island states, because while we're not a UN organization, you will see that our member states are only about half of the UN. I think there are maybe 194 countries now. We have half of those as members of GEO. But I want to talk about the role of participating organizations. There are 77, and if we look at the next slide, you'll see those 77 participating organizations. Clearly, I've heavy bolded IAF and UNESCO, co-hosting, co-sponsoring the conference today, but I've also circled or put ovals around a couple other key participating organizations that I thought might be making contributions to the conference this week, although I realize that I should have also circled Secure World Foundation right here. They are in the audience. So each of these participating organizations has some responsibility for coordinating their member states. And so from a GEO perspective, all we are interested in doing is leveraging the coordination that's already going on by these participating organizations. We are not interested in duplicating the coordination mechanism that these organizations are performing. And I would like to just particularly note IAF, because this top row of participating organizations actually were just acknowledged in January at our ministerial meeting. But our members, our governing authority said, well, listen, if you really want to influence the uptake of Earth observations, you've got member countries, member states of the United Nations at the table. You've got participating organizations, which are either UN organizations or international associations, intergovernmental mechanisms, but you need to go farther. And the next slide will show what our governing body said. You've got to bring the private sector into the mix if you want to influence the uptake of Earth observations. So we, GEO, are taking a very broad view of the private sector. It means all of those before. But for this slide, let's just look at the commercial sector, because that in and of itself is quite broad. The top tier shows private sector data providers. The middle tier may show those companies that are just interested in adding value to the data that's collected, either by governments or by the private sector in the first row. And then at the bottom row, you've got your most downstream users in the private sector. So that could be your agricultural users, your Cargills, your John Deeres, could be your energy users, it could be your water users, downstream private sector users. So we obviously, from the first definition, which is the not-for-profits, the NGOs, the development banks, or the commercial sector, It is not going to be a dialogue that's a one-size-fits-all. Each of these entities have different needs and expectations and uses of Earth observations, and that's the dialogue we are trying to negotiate. Next slide. So let's just go into the use case for agriculture right now. This slide shows that we are spending time talking about crop information for decision making, influencing decisions. You'll see a number of countries, Canada, China, the European Commission, France, Japan, Kazakhstan, India, Mexico, Russia, and the USA that have come together to willingly work on a particular project, and a couple participating organizations, in this case CS, the Committee on Earth Observation, Satellites, and the Food and Agricultural Organization. The slide or the graph actually, the map actually just shows a deviation from norm. So it's looking at a vegetation index on a particular day, August 13th, 2012. So one day, but that day compared to a 10-year average. And the color shows in reds and orange and browns vegetation that's worse on August 13th than the 10-year average, or green areas, the rice areas, are actually a little bit better on August 13th than they were compared to the 10-year average. Well, when the G20 agricultural ministers saw some information like this, they said, you know what, we really ought to bring the assets of, in this case, GLAC, GEO's Global Agricultural Monitoring Effort, together with FAO's AMIS, the Agricultural Marketing Information System. And can you use Earth observation information, space and ground, to do a better job of predicting production forecasts so that you could put a more stable pricing policy into place? So if we look at the next slide, you will actually, this just happens to be an example of monthly wheat prices from 1960 out to a couple years ago, 2011. And first of all, the slide shows a lot of changes. While we had a pretty stable situation of pricing from 1960 up to 72, after that, it really was quite sporadic. Now, there are a lot of factors that take into effect, but you will clearly see the price hikes because of droughts, whether they're in Australia or the Ukraine, Russia, but substantial shifts. In fact, 3 times the shifts in price as it was back in the 60s. Let's go to the next slide, because even in this day and age, let's look at an aggregation of the major wheat producing countries for 3 years, 2010, 2011, and 2012. So what you'll see in red are the production forecasts as they go through the season. What you'll see in blue are the prices. So clearly, you've got your inverse relationship between production and price. When forecasts were high, price was low. When forecasts were low, price was high. But look within a given season for the billions of dollars that are being invested in agriculture globally. These are still relatively large swings within a given season. So the effort here is how can you bring space-based and in-situ observations to the table earlier in the growing season so that you could start to do a better job of leveling out that red line, leveling out the production forecasts. And just like with weather forecasts and the substantial improvements that have been made over the last 20, 30, and 40 years, we ought to be able to bring that same kind of accuracy improvement to production forecasts if we want to stabilize prices to create a more food secure world. So you'll see a pretty good rotation of soybeans, corn, sorry, let's go back. 2004, still soybeans, 2005, corn in that rectangle. All of a sudden, the rotation to soybeans has stopped in 2005 when the U.S. put some ethanol legislation in place so that farmers were given subsidies to grow corn. So the rotation stops in 2005. You'll see corn all the way out to 2012 when the subsidies ended, and now soybeans are coming back into the rotation. So I think there are a couple of things here. Pretty amazing that we can see how regulations or legislation on the ground can be observed from space. Clearly, farmers know that a rotation of corn, soybeans, corn is much healthier for the long-term producing ability of the soil, so that the nutrients of one crop can recharge or replenish the ones that were depleted from the year before. But I think what's also important about a slide like this is we don't just collect satellite observations for today. The fact that this information can be observed in archives back to 2000 or even before that is essential, because just like with the archaeological exhibits, what you want to do is be able to observe landscape change over decades, not just over days, but over decades. Let's go to the next slide. And then, although this graph is kind of dark, what it does show is coming up a scale. This happens to be the Iberian Peninsula, again using Landsat data to show forest change, green, no change, red, deforestation over a 10-year period. I don't know how many hundreds of thousands of scenes it would have taken to generate this particular image, but this analysis was not available before the archive was released free and open, so that we could start going in and doing substantial landscape change analyses. So one of our objectives about advocating for broader data is shown in a graph like this. The next slide, we'll just take it up one more scale, and this is a new map of standardized terrestrial ecosystems for Africa. So you need space-based information, you need ground-based information if you want to do any serious analysis of landscape change. The last slide, let's go to the next slide, because we do want to, let's click one more time. We do have a homepage, we do have a portal that's being hosted right now by ESA, the European Space Agency. If we go one more click on the slide, you'll see something called, first of all, in the middle of the slide, you'll see something we call GeoData. It's a discovery and access broker. So for many, first 5 or 6 years of our existence, we were out trying to find every last data set and get these entities that you happen to see on the left-hand side of the grid to, in fact, register their data in our system. After 5 years, we realized that was not the way to go. We instituted something called this Discovery and Access Broker, which is just an interoperability agreement between our infrastructure on the right-hand side of the graph and all the entities that you have that may have data in the cloud. They certainly have data in archives, so that people coming into the GEO website can just, one, discover other data, and then ultimately access that other data, and then emerging involvement of the private sector in the lower right-hand slide. The next slide will show the success of this particular strategy. So as of a couple days ago, we had more than 30 brokered data providers. Those would be the entities that you happen to see on the previous slide. About 13 million discoverable, potentially accessible resources. These are data collections, data sets. They could be individual images, but each of those data resources are comprised by about 70 million individual resources that could be one satellite scene or one stream gauge. And so a tremendous amount of information is now, one, discoverable, and if those entities' systems are up and operating, those are in fact accessible. We don't take the data, we just discover it and access it, so that the data stays resident with the institution that has responsibility for QA, QC, and metadata. The next slide will show just maybe a graphic of what we're talking about in what we happen to call our GS infrastructure. Let's think about it as a hypercube where you can look at one dimension, which is thematic, data, agriculture, energy, water. We can look through time, and we can look through space. These next couple slides are just going to go pretty quickly, but let's click on the next slide. So we can look at precipitation data in Greece, a narrow spatial area, a narrow thematic area, a narrow temporal area, 1946 to 2013. Next slide. We can look at global precipitation, much larger geographic area, still a limited temporal time frame. Next slide. We can start bringing in ancillary data. This happens to be land use change data in all of Europe for a particular time period. Next slide. Again, floods, bringing some disaster data or social data. We are still looking for key partners that will bring socioeconomic data to the table. That is not one of our core competencies. Next slide. Drought in Africa or West Africa droughts over a different period of time. Next slide. Different switch. Next slide. Next slide. And the last slide. So essentially what we are trying to do, so it also represents both the opportunities and the challenges that we have in GEO. If we are trying to complete this hypercube, that is to discover and access data that exists across all the themes, across all the time scales, and across all the spatial scales. Our goal is to complete this hypercube, but you can see right now if you go in and do searches, it's really kind of a mishmash of data. It's whatever those organizations have to offer. You can go in and do searches on our infrastructure by themes, by time, or by space, but our goal is actually to complete the entire cube. I think next slide, just in closing, in January, many of you in this room were in Geneva where the ministers of those 90 countries came together and said, you know what, it's been a great grand experiment, but many of the targets have not been met. There is still much to do. So they granted another 10-year mandate to the Group on Earth Observations and actually called out a couple things that they would like us to focus on. Continue improving Earth observations worldwide. Clearly, they want the adoption and implementation of data sharing principles globally. While there have been some great successes, whether it's a Landsat story, whether it's a RadarSat story within the federal government in Canada, whether it's the Copernicus policy here in Europe, there have been some good examples. Much more needs to be done globally. We need to advance the information system, and we need to cultivate global initiatives like that GLAC, that agricultural initiative that I talked about. In closing, I want to draw a little attention to an apathon that's being launched right now. It was launched a few weeks ago. Registration is open until July 31st. The applications have to be submitted by August 31st. It's open worldwide, any non-commercial entity, individual or team. So please redistribute this to your students, to your communities, because if we really want to ensure the uptake of Earth observations, we've got to kind of tap in to creative applications that we have not even thought of yet. And I will say that thanks to the U.S. Agency for International Development, USAID, came in and is putting up $20,000 for cash prizes. The first prize will be on the order of $5,000. So that's a substantial amount of money if you know some individuals out there who could come up with a really creative application. We'd like to pay particular attention to the developing world for those applications, where in many parts of the world people have better access to cell phone technology than they do clean water. So the last slide is to remind all of you that are either participating organizations or members in GEO. Our annual meeting is coming up in Libreville, Gabon, the 13th to 14th of November. Our website down at the bottom. I'll end there. Thank you very much.
Dr. Santini Malinga is the first Chief Executive Officer of the newly established South African National Space Agency, SANSA. He is a space physicist by training, with a doctorate from Rhodes University, where he started his lecturing career. In 2002, he joined the University of Natal and subsequently became the Dean's Assistant at the University of KwaZulu-Natal. And in 2007, Dr. Malinga was appointed the manager and later managing director of the SANSA Space Science Directorate, which was previously known as the Hermanus Magnetic Observatory, a national geospace science research facility that operates a wide observational network in South Africa and also in the Antarctic. Dr. Malinga has served on a number of important committees, including the South African Council for Space Affairs, SACSA, the National Committee for the Committee on Space Research, OSPAR, and Scientific Committee on Solar Terrestrial Physics, COSTEP. Dr. Malinga, you have the floor.
Good morning, ladies and gentlemen. It's a great pleasure for me to be here, to be part of the plenary this morning. And I'd like to thank UNESCO and IAF for having invited me to this very important conference that we'll be having for the next 3 days. What I would like to talk about today is what I've referred to as the irony of humanity's success and the potential contribution of space applications and addressing the associated challenges. As humanity, we have advanced quite a lot. And for us to understand it, is to think about how this morning would have been if it was about 50 years ago, 100 years ago, or a couple of centuries back. We wouldn't be sitting as we are today with a gadget in our pockets that has the processing power that supersedes yesteryear computers, that in those days would fill a room or be bigger. Even in other areas, when you think of agriculture as an example, if it was 50 or 100 years ago, we'd probably be using farming implements that are very primitive. Some of us have never seen a sickle as an example. That's one of the farming implements that was used in the past. Nowadays, we're using very sophisticated instrumentation. We've mechanized our agriculture quite extensively. And we've improved in a number of ways in the way that we do agriculture. Irrigation, as an example. We have GMOs, as an example. And we've changed how the game of agriculture is pursued. In medicine, there are a number of advances that we've made as well. If you were to draw your memory back to the time when there was no anesthetics, a simple operation on your toe today would have been a different proposition altogether. You probably could die. Let's leave alone the pain that you suffer in the process of a simple operation like that. Nowadays, such an operation is standard procedure. You do it without even thinking about it. This and many other challenges and improvements that we've achieved have really transformed our world. In agriculture, our production has exponentially increased, threefolds to what it was in the past, in the 1950s. Our life expectancy has also changed from 50 years in 1950 to around 70 today, as we're seated here. This is just some of the challenges, of the improvements that we have achieved. In agriculture, our production has increased quite extensively. As Barbara was showing us, we've changed how we do our agriculture. We don't allow our land to be fallow. We can farm all the year around these days. That has come with many challenges in our world today. And it's for that reason that I sometimes talk about the irony of our success. What is our success that led us to today? Some of the things that we achieved are actually threatening our own existence. I would like to talk about some of the changes that have happened in our universe today that are a threat to our own long-term sustainability. When one looks at the level of extinction of our biodiversity today, it's quite huge. Terrestrially and in water, the current estimations of our extinction of our species range from between 25% to around 80% today. We travel quite a lot, and in the process of doing that, consume a lot of energy. What has that led us to? We emit in excess, energy alone, when you look at energy, it emits in excess of 40% of carbon emissions today. The global population is increasing, and current estimations are that it will increase from 7 billion today to around 9 billion in 2050. And the important thing one has to note is the biggest change is projected to be in developing countries. That is a huge challenge for us, or a person like myself from the African continent. In Africa alone, the population is expected to double from 1.1 billion to around 2.3 billion. And this is premised, and this is very important, on the total fertility rate decreasing from the current 5 children per woman to around 3 by 2050. If that happens, it might be more than double the population in Africa. This increase in our population comes with many, many challenges. Pollution, urbanization, scarcity of resources, amenities like water, sanitation, to name just a few. The Food Agriculture Organization estimates that due to this expansion in our population, the production, agricultural production has to increase by at least 70% from the levels of 2005 to 2007. As you are well aware, any more agriculture in terms of, for instance, cattle that are pollutants in terms of greenhouse gases, to the chopping of trees to make way for grazing land and agricultural farming, those kind of changes create an immense strain on our environment. As we know that agriculture amounts to about 25% of greenhouse emissions today. The second challenge is that of transmitting the data from one point to another. And the third one is that of transmitting the data rapidly. These and many other challenges are very prominent on the African continent. However, as a continent of Africa, I believe that we're standing at the door of opportunity today. Why do I say so? Africa has a youthful population that is eager to face the future and make its mark. Africa is blessed with natural resources, and new resources are discovered daily. Africa's democratic rule is growing, and there is huge development in many African countries. Africa has recently enjoyed sustained economic growth, and there's a huge development in a number of countries. Africa has an opportunity to leapfrog in terms of technology in a number of areas. As an example, our rural communities have moved from a state of not having any communication lines in terms of telephones straight to having mobile phones. Barbara was talking about more people having mobile phones than quality of water, and that's a fact. And that's what's happening in Africa. There's opportunities for Africa to squander or to use. And I believe that we can. And there are signs of hope and signs that we can do this. There are a number of new inventions that have come from Africa, and one thinks about M-Pesa as an example in Kenya, where we've used, as Africans, the fact that a large number of our population is unbanked, no banking accounts. And we've used cell phones to ensure that they transact on a day-to-day basis. In South Africa, we've come up with the with the Advanced Fire Information System, AFIS, a satellite-based system that is used to warn farmers, energy utility companies, in our country about fires, and is extensively used globally for fire warning systems through SMS. And therefore, with those words, I believe that we're standing at the door of a huge potential globally and specifically as an African people. I thank you.
The fourth speaker of this morning plenary session was supposed to be Claire Joly from OECD. Unfortunately, Claire Joly was hospitalized earlier this morning and cannot make it to this conference. Of course, I will communicate with her and wish her a quick recovery, but she has accepted that I briefly present to you the content of the keynote speech that she had prepared and that is loaded already on the computer. So let's move on. Claire Joly, in fact, is the head of the OECD Space Forum in the OECD Directorate for Science, Technology and Industry. She has worked many years in business strategy and policy analysis, both for public and private organizations in aerospace and defense, both in Europe and in North America, before she joined the OECD in 2003. So she has a dual background in international relations and finance from the University of Versailles and Cornell University, and also in aerospace engineering with a focus on space application. She is an alumna of the Institute for Higher National Defense Studies here in Paris, Institut des Hautes Études de Défense Nationale, and she's a member of several professional organizations. I will add that she is also a member of the French Navy Citizen Reserve with the rank of Lieutenant Commander, which is Capitaine de Corvette in French. So I will briefly present to you the presentation that Claire Joly has prepared, which is called Space Application and the Economy. First of all, as you know, the OECD, the Organization for Economic Cooperation and Development, is an international economic organization. It's a global forum in which government representatives work together to address the economic, social, and environmental challenges of interdependence and globalization. OECD is a very powerful source of economic statistics, which is used worldwide. And in fact, OECD as an organization doesn't have any vested interest in the space sector, but it has a recognized expertise in the economics of space. The work of the OECD in the Space Forum started following a call from governments and institutions for a neutral economic analysis of the space sector, complementing the existing international platforms. And its mandate was to better identify the statistics in the sector and investigate its economic dimension. There is a steering group of this activity, supervising the activity, which includes representatives from Canada, from Switzerland, Germany, France, Italy, Norway, the UK, the United Kingdom, the USA, as well as the European Space Agency. The OECD is, of course, involved in very much in international cooperation and is leading a constructive dialogue with other space agencies, international institutions, academia, the private sector, and industry associations. As you all know, and you have heard this morning, space is changing, evolving very fast. Some numbers here on the left-hand side of the slide, you will see that more than 50 countries, in fact today it's probably closer to 60, are operating satellites, and about 9 today have been able to actually access to space with their own launcher capability. OECD has published already a number of papers which have to do with space, and for example, the space economy at a glance in 2011, the OECD handbook on measuring the space economy, and I would recommend you to refer to these publications to see a little more in detail the work that the OECD has been done in this area. For example, the OECD has been trying to answer the question, why do countries invest in the space program? And these are examples of motivation for developing a space program and how it evolves with time. For example, in year 1, you will see on the slide that the prestige and motivation for developing dedicated military technology ranked very high. But as the program develops in the country, the role of prestige and military technologies motivation tends to diminish. And then you will see that there is strong motivation for the development and the sustaining of a skilled workforce, for the development of space application to the top right, for the development of expertise in specific technologies and application or science. And of course, this continues to evolve over time. Now, one must remember that you don't develop space technology for the sake of space technology. You develop space technology, space infrastructure, and the associated services because these are tools. They are tools to reach a number of national and international policy objectives in view of societal challenges that need to be addressed, and Dr. Salim addressed this very well earlier on. The use of natural resources, the challenges to environmental management, the increasing mobility of people and goods, the uneven progress towards the information society, the management of waste, etc. For example, we all know that urbanization is a global phenomenon that will continue for decades to come. The figure to the left of the slide shows the percentage of, not the percentage, in fact the actual number of urban population from 1950 to 2050, and that is a number which is going to be increasing to probably about 5 billion, while the rural population will tend to stabilize and then slowly go down to about 2 billion. And the figure to the right shows or illustrates, I would say, the urban concentration in European regions, with peaks showing where the urban population density is very high. One refers sometimes to the potential impact of solar storms, which could affect all this infrastructure or a large part of the infrastructure. This figure to the right is from the geomagnetic storm that took place in April 2000 and illustrates the region of the world, mostly in the northern latitudes that were affected by the storm. Right now, the OECD is Space Forum looks at two areas of work. One is investigating the potential socio-economic impact derived from selected space application, such as case studies that are selected in order to focus on the economic impact, and also examining the broader economic impacts of national space investments, linking with, of course, other activities in the organization, the OECD, such as innovation policies, impact in the economy of public R&D, etc. And there is a technical workshop taking place this month in OECD. As part of the economic impact of space investment, one looks at the new commercial activities that are developing based on new products and new services coming to the market. The productivity or efficiency gains of in various parts of economic sector thanks to the use of space-based services, for example, precision farming, fisheries, land transport. The regional economic growth that can result from the development and sustainable space industry, and also the cost that can be avoided by the smart use of these technologies. Two specific sectors are being addressed right now. One is the fishing industry, looking at the efficiency gains and improved control of resources as a result of satellite navigation usage in ships and in surveillance of maritime zones. And the other one is prevention of floods and management of flood situation, which lead to avoidance of cost and possibly savings in terms of managing the cost, the high cost of floodways. There are specific issues that the Space Forum is looking at. For example, reviewing the data policies for Earth observation to increase benefits. This was addressed in part by Barbara's speech earlier. And this figure shows the distribution of data policy in terms of free access to data, or mostly free, or partly free, or commercial approach. The range of societal challenges to tackle in this Space Forum is growing. Space applications are no luxuries, they have a role to play. The OECD plans and ambitions to to improve the knowledge base and applications, to provide both know-how and valid experience to practitioners, and evidence-based information to decision makers and citizens on the benefits, but also on the limitation of space application. And for that matter, there is a major OECD symposium that will take place next October in Paris, here in the OECD premises, called the Economic Impacts of Space Technologies. And I believe that closes this brief summary of Claire Jolie's presentation. And of course, if some of you have questions that you would like to address to Claire Jolie, I'll be happy to take your name or your business card after this session and relay your questions to her. Thank you very much. Dr. Wanda Watson-Hyde is the Executive Secretary and Assistant Director General of the IOC, the Intergovernmental Oceanographic Commission of the UNESCO. Headquartered in Paris, IOC UNESCO has a mandate within the United Nations system for ocean science, observations, data, and information exchange and services, including global tsunami warning systems. It is also the competent international organization for marine science under the United Nations Convention on the Law of the Sea. As of March of this year, Dr. Watson-Hyde was also named as UNESCO's Interim Assistant Director General for Natural Sciences. From 2001 to 2009, Wendy Wilson-Wright was Assistant Deputy Minister, Science for Fisheries and Oceans, Canada in Ottawa, Ontario, and she was responsible for providing the policy direction and scientific leadership for all science activities in the department's 15 science institutes throughout Canada. She is or has been a member of several boards, including the Canadian Foundation for Climate and Atmospheric Science, Ocean Networks Canada, Arctic GLAC, and the Strategic Advisory Board for the European Union Joint Program Initiative on Ocean. A Killam Scholar, Dr. Wilson-Wright holds a PhD in Physiology from Dalhousie University in Halifax, Nova Scotia, Canada. Wendy, you have the floor again.
Thank you. I am delighted to address you a second time this morning at this Global Space Applications Conference, and this time to talk to you about the Intergovernmental Oceanographic Commission of UNESCO and the importance of space applications to IOC's work. Is there any particular place I have to point this part out? No? Okay, so much of the ocean is over the horizon and, as you know, is inaccessible to direct observation. You know, when the Intergovernmental Oceanographic Commission, or the IOC, was formed 54 years ago, seagoing oceanographers were, of course, confined to a view of the ocean which stretched barely 7 miles to the horizon. Now, satellite images of a wide variety of ocean properties like ocean temperature, sea surface color, and sea surface height routinely reveal to scientists and the public an ocean of indefinite variety marked by swirls and colors and driven by complex currents and eddies. We can see the warm tongue of water extending along the equator, marking the El Nino. We can monitor upwelling along the coasts of California and Chile through chlorophyll color, and we can image a harmful algal bloom moving toward the beach. So the ocean is no longer simply the uniform blue area between the continents that we see on globes, but is more and more appreciated for its complex role in our world's climate and biosphere. Now, going to sea in ships is still an extremely expensive way to do science, and a ship can only largely observe what is immediately below it. Satellite information has, from the beginnings of space imaging, filled in the areas between ship tracks, allowing extrapolations of onboard measurements to be made to wider areas of the ocean. On the other hand, we recognize that in situ measurements made by those ships are essential to calibrate and ground truth satellite data. Ocean research has grown with satellite technology, but satellite products will always require those data that can be obtained only with a water bottle and ocean-going laboratories. But the Earth truly is an ocean planet. To begin with, the ocean covers 71% of Earth's surface. It accounts for 97% of the Earth's water and 96% of the living space. It provides 2/3 of the value of all the natural services offered by the planet and the oxygen for every second breath that we take. It has cushioned the blow of climate change by absorbing 25 to 30% of the anthropogenic carbon emissions and 80% of the heat that's been added to the global system. It regulates our weather, and it provides food to billions of people. The ocean and its resources are part of our common heritage, and an important part of many cultures whose beliefs and practices are closely associated with the marine and coastal environment. In fact, 49 UNESCO World Heritage Sites have been inscribed for their coastal or marine values. So the ocean is, in fact, priceless. Worldwide, the ocean is a critical economic resource. The value of marine activities globally is estimated at 5% of GDP, or close to $3 trillion US.
90% of all goods in the world are shipped by sea, so no doubt the clothes that you and I are wearing got to us somehow by the ocean. More than 40% of the human population currently lives in the coastal zone, that's within 100 kilometers of the coast, and there are some projections that say that by 2025 this is going to reach 75%. Fisheries provide 4.2 billion people with more than 15% of their average per capita intake of animal protein, and fisheries and aquaculture provide more than 180 million jobs. In fact, the ocean supports many industries, not only fisheries and aquaculture, but others like shipping, oil and gas, marine and coastal tourism, cruise ships, submarine cables, etc. The ocean is an integral part of our planet, and it's an absolutely essential component of human lives, livelihoods, and the environment that sustains us. Yet despite our reliance on marine resources, ocean acidification, climate change, polluting activities, and overexploitation of marine resources have made the ocean one of the Earth's most threatened ecosystems. And I'm going to give you just a few examples of how human activities threaten the ocean and its precious resources. As I mentioned, the ocean absorbs more than 26% of all the carbon dioxide emitted to the atmosphere from human activities. The result is increased acidity, that is, a lowered pH of the ocean. This can reduce the availability of calcium for plankton and shelled species, threatening their survival. Now, since many of these organisms serve as the base of the marine food chain, the potential impact of acidification on entire ecosystems can be dramatic, and in fact, in business as usual scenarios, the ocean could become 150% more acid by the year 2100. Land-based sources account for approximately 80% of marine pollution globally. Excessive nutrients from sewage outfalls and agricultural runoff have contributed to the rise in the number of occurrences of harmful algal blooms, or HABs. These are phenomena which are caused by both toxic and non-toxic phytoplankton that displace indigenous species, alter habitats, and accelerate oxygen depletion. In addition, the unchecked dumping of waste from human activities into coastal zones has led to a dramatic increase in the number of what we call dead zones. These are hypoxic areas, from 49 in the 1960s to well over 400 now. This has resulted in the collapse of some ecosystems, and nowadays more than 245,000 square kilometers are affected. This is equivalent to the size of the United Kingdom. Over 80% of the world's 232 marine ecoregions have reported the presence of invasive species, which is the second most significant cause of biodiversity loss on a global scale. The world's marine capture fisheries are in a severely troubled state, and the FAO estimates that 85% of fish stocks are fully exploited, overexploited, depleted, or recovering from depletion. In fact, the ocean faces a multitude of interconnected threats that is unprecedented in modern human history. Now, there are some classic examples of the space perspective on some of the threats to the ocean that I've just mentioned. The most iconic image of climate change today is probably the time series of Arctic ice coverage built by satellites since 1978 and continued today with Cryosat-2. These images have shaped our understanding of the remarkable changes occurring in the Arctic Ocean and have spurred the public and government to support at least some new initiatives for polar research. Satellite data can be used to identify and monitor red tide events, such as this one that is spreading from the Gulf of Oman into the Persian Gulf in 2008. UNESCO, through its IOC and its Intergovernmental Panel on Harmful Algal Blooms, has established an international committee and just co-organized an international conference to address the issues of these toxic blooms and desalination with the Middle East Desalination Research Center, regional and local partners. And the two-day HABs and Desalination Conference held in Muscat, Oman, just in this past April, discuss the state of desalination technology, and foster dialogue among scientists, engineers, and managers. Satellite imagery has, of course, also been used to monitor threats to World Heritage Sites, such as the Great Barrier Reef in Australia, shown here, which has been threatened by port development and associated dredging and ship activity, as well as climate change and pollution. Now, the IOC vision responds to these issues by recognizing that a sustainable blue planet will benefit all nations, and it's a global responsibility to establish sustainable global governance for a healthy ocean. In particular, the IOC vision highlights the need for strong scientific understanding and systematic observations. Our medium-term strategy has 4 high-level objectives shown here, including promoting healthy ocean ecosystems, developing early warnings for ocean hazards such as tsunamis, assisting societies in developing resiliency to climate change and variability, and applying enhanced knowledge of emerging issues for societal benefit and improved governance. The IOC achieves its high-level objectives by engaging its member states and the larger ocean science community in different programs that fall into the functions that are shown here. And those functions include fostering research to strengthen knowledge, maintaining, strengthening, and integrating global ocean observing data and information systems, developing early warning systems, services, and preparedness, supporting assessments and information to improve the science policy interface, enhancing ocean governance, and developing the institutional capacity in all of the functions above as a cross-cutting function. The main application of space technologies to the work of the IOC is in satellite communications, which allow many remote components, human and mechanical, of various systems to communicate. And this, of course, relates to all the functions of the IOC. Now, ocean observation systems are coordinated by the IOC through the Global Ocean Observing System, or GOOS, and related programs. Through seeking international agreements on the fundamental requirements of ocean observation systems by identifying essential ocean variables, GOOS becomes the framework of unified ocean observations, which encourages data sharing and utilization. Now, as I mentioned, IOC is the lead for GOOS, and as you may have noticed on one of Brian's slides, GOOS is a participating organization in GEO, and I'd say a very active participating organization. It's quite a complex system, and you can see its in situ components here. It's made up of observations from many different types of platforms: research and volunteerships, moorings, profiling floats, surface drifters, and tide gauges. And the map in the center of this graphic shows you a snapshot of where these observations are taken in the global ocean. And you might notice that the North Atlantic is particularly well served, whereas other parts of the global ocean are not. Now, these components are complemented by surface observations of the ocean physics and color from satellites, as seen in the left part of this slide. The data from these observations feeds into data management systems and the generation of products to reach users, having impacts in science and more directly and more importantly for society. Now, the observations themselves are funded by national research and other ocean observing funding, and many of these networks are coordinated through the joint World Meteorological Organization IOC Technical Commission for Oceanography and Marine Meteorology, or JCOM, which in fact is unique within the UN system. JCOM works with the operators from many countries of the elements of the Global Ocean Observing System, providing coordination of data streams, standard setting, observation best practices, advice on deployment opportunities, and development of data products. Along with support of the International Network of Drifting Buoys, Moored Buoys and Time Series, and Ships of Opportunity, JCOM has been instrumental in the growth of the Argo subsurface profiling floats. Now, Argo is quite cool, I would say. Argo collects high-quality temperature and salinity profiles from the upper 2,000 meters of the ice-free global ocean and currents from intermediate depths. The data come from battery-powered autonomous floats that drift at depth for 10 days at a time. After 10 days, the floats rise to the surface over a period of about 6 hours while measuring temperature and salinity. Satellites then determine the position of the floats when they surface and receive the data transmitted by the floats, and of course disperse that data. And the floats then sink down to drift until the cycle is repeated. In November of 2012, the Argo Profiling Float Network collected its 1 millionth profile of vertical temperature and salinity. This is twice the number of profiles collected by all the research vessels put together in the 20th century. Now, in its second decade, the Argo system has proven to be one of the most transformative developments in oceanography, enabling a detailed, real-time, three-dimensional view of ocean circulation on a global scale. But I'll repeat that coastal sea level measurements are notoriously difficult to interpret, since the measurements can be dominated by local geophysical changes. Satellite imagery and altimetry, when combined with coastal ground truthing, has been used to map sea level change across whole ocean basins. And with the altimetry data, accurate to the millimeter, the effect of changes in local wind forcing can be accounted for, and global sea level rise can be accurately determined. Without these satellites, coastal measurements would not be able to deliver this key index of climate change. Now, the central figure here shows the communication required by the various components of the GLAC system, including the satellite linkage. The map in the upper left shows the array of monitoring stations, and the European map indicates sea level anomalies in Europe which occurred in 2012 as recorded by GLAC. These changes, while happening around our globe, are not uniform. In fact, the IOC has developed and promoted ICAM as a tool to pursue sustainable development, which is a goal, of course, of Rio+20 in coastal zones. Also related to integrated management, marine spatial planning, or MSP, is a public process of analyzing, allocating the spatial and temporal distribution of human activities in marine areas to achieve ecological, economic, and social objectives that usually have been specified through a political process. No single country can develop basin-wide tsunami detection systems. Such systems depend on international collaboration, which is embodied in formal commitments with the official support of governments. IOC provides secretariat support to the Intergovernmental Coordination Groups, or ICGs, that have been established for the 4 regions in the world. These are Pacific Ocean, the Indian Ocean, the Caribbean, and the Northeast Atlantic, Mediterranean, and connected seas, to facilitate the coordination of the development commitments. Now, under each ICG, there are a number of technical working groups that deal with detection networks, hazard assessment, preparedness and awareness at community level and for schools. IOC has provided and continues to provide technical assistance and capacity development to the elaboration of tsunami warning systems. Improving these systems goes hand in hand with improved scientific understanding about tsunamis and their socioeconomic impacts. Tsunami science and enabling research and policy development are critical elements in this process. But I should also emphasize that the tsunami warning systems build on partnerships with other organizations, such as the WMO for GTS, many scientific seismic networks, and the CTBTO, that's the Test Ban Treaty Organization for seismic observations, the UN ISDR, which is for disaster reduction, civil protection and emergency management authorities, and many national science institutions for opportunistic capacity and awareness raising. And just to mention a little bit about awareness raising, the education and public awareness elements of the tsunami warning system have certainly been a critical element of its success. In addition, the warning system includes a text message warning that can be sent to subscribing citizens' cell phones, really taking communications to new levels, from scientific measurements to government decisions to individual warnings. And coming to capacity development, which is, of course was mentioned earlier by Sandy Malinga, and the need for capacity development in emerging countries. Emerging economies, including small island developing states or SIDS, have an urgent need to monitor and manage their coastal waters and their exclusive economic zones. Pollution, fisheries exploitation, sea level change, and coastal hazards, such as those I mentioned, tsunamis, storm flooding, have outsized impacts on these nations. Many, as mentioned, have limited abilities to make direct observations, and they find great value in their ability to access satellite products which cover their territorial seas. The IOC has programs which seek to develop the ability of SIDS and developing nations to work with advanced technologies and opportunities available from satellite services. Training and consistent maintenance of basic communication facilities are very high priorities for these countries. Now, in terms of capacity development for ocean management, the IOC made a voluntary commitment at Rio+20 on building capacity, global capacity for marine sciences, observation, and transfer of marine technology. Following this commitment, we carried out a survey and a sample of 20 member states. That survey was completed and presented at IOC's 27th Assembly past June, and the results now form the basis for a new IOC capacity development strategy, which will be presented to the IOC Executive Council in July of this year. The goals of this capacity development strategy of the IOC are to promote knowledge and capacity of developing nations, to bolster scientific understanding of ocean and coastal processes, to reduce the risks and impacts of ocean-related hazards, take climate change adaptation and mitigation measures, develop and implement policies for healthy ocean ecosystems by reinforcing and further developing member states' institutional capacities to protect and sustainably manage ocean and coastal resources. Now, space applications clearly can and should play a large role in all of this. So in closing, I would like to come back to the importance of the ocean to the world, and in particular to the very things that drive humankind forward. The ocean community is indebted to satellite imagery for demonstrating that we do really live on planet ocean, as aptly pointed out here by Arthur C. Clarke. And as an aside, I agree with him. I do think that the planet is misnamed, and if I knew who to take it to, I would be pushing for planet ocean. However, the slow damage to our ocean environment will not be solved easily. Our most potent weapons in the struggle are, of course, information, knowledge, and public awareness. Too often, solving problems which are over the horizon is postponed to another day. It is essential that the challenges of the ocean be understood to be the challenges for all humanity. The understanding that satellite imagery brings to the public discourse has been essential in raising attention to the ocean and to its issues. And I sincerely hope that this attention will now translate into positive action. I thank you very much for your attention, and again, wish you an excellent conference. Thank you very much.
So any urgent question that you would like to address to the speakers this morning? We have about 10 minutes that we could spend with this. And we have microphone available for those who want to raise a question. I have so much light in my face that I can't really see the room.
Hi, this is Barbara. Sorry to bother you. Was wondering why I was listening to your very interesting presentation. if these data are accessible for free.
Yes, good question. So when we talk about 30 brokered systems, 30 million, and then 72, all of those, almost all of those are, by and large, the vast majority open, freely available. We think there's a lot more out there, and that's why we're trying to work with other countries to similarly open up their assets for the government collected data. So basically our philosophy is that the governments, the taxpayers paid for the large investments to build the satellites, to put the stream gauge network in place, to put the Argo floats that Wendy just talked about in place. And so the bulk of the investment was in the infrastructure. You shouldn't create any barriers for citizens to get access to the information that's derived from that infrastructure. So yeah.
Thank you, Barbara. And by the way, the question was raised by Maria Antonietta, who is the Vice President of the IAF. So thank you, Maria Antonietta. Other questions in the room? Mario, you have? There is one over there. Yeah, okay.
Thank you.
Can you introduce yourself?
Yeah. My name is Joy Agene from the Nigerian Space Agency. My question is for Barbara. Yeah, because we are mostly into Earth observation, the Earth observation, and I noticed when you were displaying the map, Nigeria is not, I didn't really see a map. So do you have this group on Earth observation in Nigeria too?
Yes, Nigeria is one of the 91 members. Senegal has just recently joined this week, so Senegal may not have been covered or colored on that map, but Nigeria is a member. Guyani Abayu is our geo principal, but be happy to put you in touch with anyone because what I should have said is that we are encouraging national and regional geomechanisms. That is, regardless of which agency you're in within a country, we would love to see you on the geo delegation from that country so we can follow up with you offline. And then just one other point, for anyone in the audience whose country was not shown in red, by all means come up and catch me at the coffee break. We'd love to talk to you about geo membership.
Do you have another question? Yes, okay, Maria Antonietta has another question.
Sorry, it's always from my heart. I was really astonished by the last presentation about how important is the water for our life. I work in exploration on Mars, and the motto, the current motto of the Worldwide Space Agency is follow the water. We look for water in the other planets. So I think that we shall, as a minimum, take a good care of the water we have around and the ocean. And so, thank you for your presentation. So, it's not a question, it's a comment from my heart, as always. Sorry.
Mario Antonietta is a very good comment. And in fact, I can reflect on some discussions that I remember having in the 80s and 90s about the purpose of exploring the other planets. And for example, Venus is a very good example because Venus is a place where the greenhouse effect is so strong that it's about 400 degrees at the surface. And if we are not very careful, we might end up like Venus. On the other hand, Mars is the opposite example, where the atmosphere are more, to a large extent, escaped. So we have various models of how a planet can evolve. And this can also help us understand how our own planet will evolve indeed. And I recall that I signed in the 80s, maybe early 90s, I signed a reception agreement with the CRISP in the National University of Singapore, which is a center for remote sensing and image processing, where they receive the satellite data and process the satellite data. And I would like to testify to the fact that this team in Singapore was doing, and probably still is doing today, extremely good work in using satellite data in two specific areas of application which are direct interest in this conference. One of them was monitoring the forest fires, mostly taking place in Indonesia, but affecting the whole of the Malaysian peninsula, including Singapore, leading to very poor visibility to such an extent that sometimes the airport had to be closed. And they were using satellite imagery to produce daily assessment of the situation with forest fire in Indonesia and providing this daily assessment to the local authorities in Singapore and in Malaysia. That's one example. And this was done daily during, of course, the forest fire season. Extremely good work. The second good application that I saw was also in the field of marine application, and they were using SAR data from the European Space Agency ERS-1 satellite and the Canadian RadarSat satellite to monitor the shipping lanes in the Strait of Malacca. And this led them also to produce daily, or in fact twice daily, updates on the shipping activity in the Strait of Malacca. This, of course, in relation to smuggling, but also to potential oil spills or other disasters of that type. This was an interesting case because we, speaking of the 90s, a small team in the University of Singapore was doing high-class application of daily interest in the Southeast Asian region, and I wanted to recall that's very good memory.